Hello, everyone. Welcome to our Statistics Solutions webinar today. My name is Justin D'Souza, and I'm a quantitative specialist here at the company. Today, we are going to cover the verification of statistical assumptions. I'll go through some examples in SPSS and kind of explain what to look for when you are verifying assumptions. If you have any questions, you can type them into the chat box. My colleague Sierra is also going to be providing some hyperlinks in the chat box if you'd like to schedule a free consultation with our specialists. During those consultations, we will give you guidance on where we can best assist with your paper and offer some solutions to help you get through the process. And we'll also send everyone a copy of the recording of today's webinar, as well as a copy of the slides. Okay. First, I'll give an overview of what we do at our company and how we can assist with your dissertation or your thesis. Then we'll discuss statistical assumptions. I'll give a demonstration in SPSS, how to verify those assumptions, and then we'll conclude with the summary and a Q&A session. Okay, on this slide, you can see all the different components of a dissertation or a thesis that we assist with, starting with topic development, framing your research questions, determining what is a gap in the literature for your topic, selecting a theoretical framework or a theoretical foundation for your study, kind of narrowing down the methodology components. Are you conducting a qualitative study or a quantitative, potentially a mixed method study if you're doing both? Then, depending on what university you go to, we help with the prospectus or concept paper. Usually universities have one of those two. Then we have the proposal chapters for assistance, the introduction, the literature review, and the methodology. So with these chapters, we can help you, like I said, with the topic development, kind of narrow down your research questions, the theoretical framework, the nature of the study, what specific design are you using, a quantitative, quasi-experimental, or qualitative phenomenology. We can help provide citations, and we can help address committee feedback as well. So then we help with the IRB forms, data entry templates. We can host a survey for you on SurveyMonkey. And for the results chapter, we can actually crunch your numbers or look at your qualitative data and thematize your findings using in vivo. For the results chapter, we use SPSS, but we also have our own company software, Intellectus, which can quickly run your analyses and present an APA write-up for you. And we assist with the discussion chapter, wrapping up your findings, connecting it to the literature and your theoretical framework, and discussing limitations of your study and implications of the findings and providing recommendations for future research. Then we assist with the PowerPoints for both proposal and final defenses and journal publications. So if you have any questions about the services, you can give us a call for a free consultation at 727-442-4290. Okay, the first assumption we are going to look at, and before I even dive into assumptions, I should give a little background on why you check assumptions. Whenever you're doing a parametric analysis, for the most part, Pearson correlations, regressions, t-tests, your data needs to meet some prerequisites in order to run those specific analyses. And it's making sure your data is appropriate to run an inferential test. Okay. One of the most important ones to get out of the way, I would say, is removing outliers. So outliers are any extreme cases in your data set that could skew the findings when you're looking at an inferential test. So it's good to consider taking those out. You always don't have to take them out, but it's something that it's useful to check it both ways, with outliers and without outliers, and see if there's a drastic difference. So I provided a citation here to Bachnick and Vidal. Their method is to standardize the scores So converting whatever measurement you're using to z-scores, and then using a threshold, remove potential outliers. So if your z-score exceeds positive 3.29, or if it goes below negative 3.29 standard deviations, that is identified as an outlying case. You can also use box plots to visually identify if there are potential outliers in the data set. And like I said, you can consider removing these cases. You don't always have to. Sometimes it's realistic to keep outliers in a data set because it depicts a true representation of how people are scoring. And sometimes that's important, when you're looking at test scores among students. It's good to keep everybody in the spreadsheet at times because you want an actual depiction how people scored. So I have a sample spreadsheet here, and if you've joined us before, you're probably familiar with it. It's a sample of car models, and we have each row is a different car model, and we have columns for different variables. This is an SPSS, by the way. So we have mileage, we have displacement, horsepower, the weight of the car. So right away in SPSS, this is already cleaned. We do have some other webinars on data cleaning that you can check out. We have recordings for those. This is already a clean data set, but we can check for outliers. And the way to do that using the first method, the Tabachnik and Fidel citation, by going to analyze, and then descriptive statistics, and then descriptives right here. And then you can just put in your variables of interest, miles per gallon, displacement, horsepower, anything that's numeric. That's important. I should have noted that before. An outlier needs to be numeric. You can't really check for outliers on something like engine type, where it's V-shaped or straight engine, or transmission type, automatic and manual. An outlier is characteristically a numeric continuous variable. So let's say we're just looking at miles per gallon and horsepower. Let's keep it simple. Then the important thing in this box is to check mark right here where it says save standardized values as variables. Once you've done that, we'll click OK, and you'll see that two new variables are going to be created. Okay, so I'll click OK. There we have it. So the two new variables have a Z in front of them, which means these are Z scores for miles per gallon and horsepower. Then, according to the citation that we looked at, if the Z-score exceeds 3.29, or if it's below negative 3.29, that could be considered an outlying case. So all you need to do is right-click on the variable of interest right here and sort in ascending order. So this is going to put the low scores, the low Z-scores first, and the high scores last. You can see that we have nothing below negative 3.29, and we have nothing greater than 3.29 mileage. And then we do the same thing for horsepower. We have nothing below negative 3.29 and nothing above 3.29 for horsepower. So it doesn't look like we have outliers for this case, so I would not make any removals. You can also do it visually with box plots, and to do that, you go to descriptive statistics and explore right here. And then you put in the same variables, mileage and horsepower, to this box here, your dependent variables. And then you'll go to plots right here. And we'll just go ahead and check mark that normality plots with tests. And under statistics, that is popping up somewhere else in my computer. Oh, here. So this box, you can then, you can check mark outliers right there, and then click OK. So this gives you a lot of output for those two variables. This is quite a useful menu doing that explore option. So as you scroll down, we will cover these for a different assumption, but then you have the box plot right here for mileage. And if you have an outlier, you're going to specifically see a point that goes beyond the whisker. So we have the box and we have the whiskers right here. If you have an outlier, it's going to be beyond the threshold of the whisker. So we don't have anything for mileage. And for horsepower, we have a potential outlier here. But if it has a circle, this is just a high score. Extreme cases will have a star next to them. So this isn't really an extreme value, but it's something to look at a little bit further. So saying that case 32, that's what the 32 means. Case 32 is the Maserati Bora, and that has a horsepower of 335. So you can see how much larger that is compared to the next highest one, which is a Ford Pantera, 264 horsepower. So that's something you might want to consider removing if you think that's going to skew the findings and you want everything to be within a certain threshold. That's just a point of interest to consider removing, but you don't have to. Okay. With all these assumptions, and if you're working on a dissertation, it's really important to narrow this down with your committee in the methodology phase. You want to know specifically what assumptions they want you to check, and you want to know what method you need to use to check those assumptions, because there are so many different ways. Just like I showed you here with outliers, you can do it objectively with a threshold of z-scores, or you can do it visually. Both methods are acceptable, but your committee might have a preference for which method to use. Okay, the next assumption, also a very important one, is the assumption of normality. Okay, so this is making sure that your variables of interest follow a bell-shaped distribution. One of the prerequisites for a lot of parametric analyses like ANOVAs or t-tests, there are objective ways to check for this. You can use a Shapiro-Wilk test, or you can use a Kolmogorov-Smirnov test. And usually when you look at significance, if you see a significant result, that is a good thing when you're doing statistics. But for these tests in particular, statistical significance is actually not ideal. You want to have a p-value greater than 0.05 for these. What this test and what both of these tests are doing is it's comparing your data to a perfect bell-shaped distribution. And if you have significance, that means your data does not resemble a bell-shaped curve, which isn't what we want. So we want non-significance, which means that your data does follow a bell-shaped curve. Then we have the visual interpretations. You can use a histogram, or you can use a normal QQ plot. If the assumption of normality is not supported, then you might need to shift your approach to a non-parametric alternative, or you can consider transforming your data, or you can remove outliers. As you can see, there are many contingencies or many alternative plans, which is why it's really important to narrow this down in the methodology chapter. What method does your committee want you to follow when checking assumptions? Okay, so for normality, we're actually going to go into the same menu for this one. We'll go to explore, and let's just use the same variables of interest for consistency, mileage, and horsepower. So before I went to the plots box right here, and you'll check mark this box, normality plots with tests. And let's do a histogram as well. So this will give you a visual interpretation for normality. And then we click OK. Okay, so one of the first, I think it's the third table here. The third table gives you the results of the Kolmogorov-Smirnov test and the Shapiro-Wilk test. And the findings may not align Okay, they might be slightly different. In this case, not really so much, but sometimes you might see significance for one test and non-significance for another. It's just how the math is done. So you could see contradictory findings. Okay, so mileage, we just need to look at the significance column for both of these. We can see for the Kolmogorov-Smirnov test, again, p-values are better if they're greater than 0.05 for this test. Okay, so we can see for mileage, we have a significance or a p-value greater than 0.05, meaning that the assumption of normality is met for mileage. And then for the Shapiro-Wilk test, likewise, we have the same finding. This is also greater than 0.05, meaning the assumption is supported. For horsepower, we have a p-value of 0.024 for the Kolmogorov-Smirnov, and then for the Shapiro-Wilk, we have 0.049. So these are both below 0.05, meaning that it doesn't appear we have a normal distribution for horsepower. And so I greatly prefer these tests because it gives you an objective determination on whether normality is supported or not with a p-value. That's really strong support. Then you can also look at visual interpretations, which are very subjective. And these findings may contradict what the normality test showed. Okay, so here I would see that, this doesn't really appear to follow a bell-shaped distribution. So if your committee prefers you to look at a bell-shaped histogram, then I would say that normality is not quite supported here visually. You can look at a normal QQ plot as well. So this is looking at your observed values and the residuals. And if your data, this is for mileage, if the data closely follows this diagonal trend line, then you have the assumption of normality is supported. So then looking at this, I would say, yeah, the data closely follows this diagonal trend line. So it does appear that the assumption is supported. Okay, so we have three different methods. We have the tests, the objective test, we have a histogram, and we have a normal QQ plot. So they could show different findings. You have to narrow down very early on what is the best method to use. What is your committee prefer, essentially? Okay. Then we go into homogeneity of variance. This is primarily used when you're looking at t-tests or you're looking at ANOVAs. When your research question is looking for differences between groups, is there a difference in self-efficacy between males and females, something like that? Or is there a difference in GPA between males and females? Then this is an assumption you need to check. Which is making sure that the data of interest is equally spread between your two groups. Usually a Levine's test is used to check for this. And the way to generate output for this, first you need to have a research question to check for this. So say we are looking at differences in horsepower based on transmission type right here. Before I do that, this is going to be a t-test because we're looking at differences in a variable that only has two possibilities, automatic and manual. So that would scream to me, hey, we need to do a t-test. Before we do that, we need to code everything with numbers. Say automatic is 1, manual is 2, like that. And then I'll go into variable view and just change this to say transmission type. Code. I actually already have that variable. Yeah, it's right here. And so we have transmission type identified. I used 0 for automatic and 1 for manual. Then we'll go to analyze. And then we'll go to compare means and independent sample test. So for homogeneity of variance, the finding is going to be given within the test itself. It's not like a separate menu I'm going to. I'm going to compare means, and we're actually running our inferential test for this one. Dependent variable, let's go ahead and use mileage. So mileage right here. And then the independent variable is going to be transmission type, making sure that you use the numeric one, 0 automatic, 1 manual. Then we need to define the groups. This means put in the numbers that you have, so 0 and 1, that. Then we click OK. Okay, and then we need to look for Levene's test. Okay, so this one box right here, independent sample t-test, has a lot of information. It gives you the result of the t-test, but before you get to that, you need to look at this box or this section right here, Levene's test for equality of variance. So again, just like with normality, significance is not a good thing for this test. What this is checking is, are the standard deviations or the variances for mileage approximately equal between the two possibilities of automatic and manual transmission? Just visually looking at it, I would say it doesn't appear to be so. You know, we can see the standard deviation for automatic was 3.83, and for manual it was 6.17. So it seems like there's a difference there, but we need to check objectively to know for sure. That's where Levene's test comes into play. Okay, so if we see a significant result, if we see a p-value below 0.05, that means the assumption is not supported. Okay, and in this case, that is the case. We don't have equal variances between our groups. Therefore, when you look at your t-test, you don't interpret this row at the top right here, equal variance is assumed. We are going to interpret the bottom row, equal variance is not assumed. So this is where you would report the findings of your t-test. You use this t-test value, you use this degrees of freedom value, and you use this p-value. You know, kind of regardless, you have similar p-values, but APA convention is going to be report the bottom row here, especially the t-test value and the degrees of freedom. Okay. So that is Levene's test for homogeneity of variance. As we just showed, if the assumption is not supported, use the equal variance is not assumed as statistic, which is this bottom row right here. Okay, then we have the assumption of linearity. This is usually checked when you're looking at correlations, Pearson correlations, or maybe linear regression. And the best way to do this is visually running a scatter plot between your independent and your dependent variables. The thing to look for is a clear positive or negative trend. Run this. Okay, so say for all of these assumptions, you need to have a research question set in stone first. So say the research question is, what is the relationship between mileage and horsepower? So then we would do a scatter plot between mileage and horsepower. Okay, and to do that, you go to graphs, chart builder, select a line graph at the bottom here. Let me just, that's the right one. Okay, you select the scatter plot. So scatter plot's right here. And then you click and drag this up to here. And then we'll put in mileage for one variable of interest. And then we'll put in horsepower for the second, like that. And then we'll click OK. Okay, and then you have what appears to be a negative trend, right? You could kind of draw a line to summarize going in the bottom right direction, meaning that as mileage of a car increases, the horsepower tends to decrease. And that intuitively makes sense. You can actually add a line of best fit to these. So if you double click plot right there, and then select elements and click fit line at total like this, that is going to give you a summary regression line that depicts the relationship between mileage and horsepower. So you can clearly see that there is a negative trend. So in this case, I would say that the assumption of linearity is supported. Okay, and then we have the assumption for absence of multicollinearity. This is used primarily when you're doing regression models, and specifically multiple regression models, meaning you have multiple predictors in your study. So you're not just looking at one predictor at a time, you have multiple factors that you're including as independent variables. So this assumption is making sure that the predictors are not strongly associated with one another. And the best way to do this, really there are a couple ways, but the primary way I see used to check this is variance inflation factors, VIFs for short. So many statisticians say that if the VIFs are below 10, then your assumption is supported, meaning that there's not a strong correlation between your predictors. So let's develop a hypothetical research question for this. First, you need to have a dependent variable. So let's say it's mileage. And then let's use displacement, horsepower, rear axle ratio, and weight predictors. We need to run a linear regression for this. And we go to analyze. And we go to regression and linear. In these two boxes, you need to put your dependent variable and your independent variables. So let's say mileage is our dependent, and we'll put all of these as the independents right here. The most important thing for this assumption, you have to go to statistics right here, and you check mark this box, collinearity diagnostics. This is going to give you variance inflation factors. Click OK and OK again. And this is going to give you the results of the regression. Okay, so very much like the t-test, the finding of the assumption is within the analysis itself. Okay, and you see this box right here, coefficients. The final column has the VIF values. And as we said over here, use variance inflation factors to check the assumption. If the VIFs are all below 10, then your assumption is supported. We can see that in the final column, every VIF is below 10, meaning that we don't have a strong association between all of these predictors. Good thing. One of the requirements to running a regression model appropriately. Okay, so those are the primary assumptions to check. I'll now open up the panel to any questions. If you have any, you can raise your hand or you can type it into the chat box. And we'll send everyone a copy of today's webinar and the PowerPoint. Give us a call if you have any questions about the services at 727-442-4290, or you can send us an email at this address right here. Do we have any questions about assumption checking? You can raise your hand or you can type it into the chat box. All right, if we don't have any questions, I'll go ahead and wrap it up then. Come join us again for future webinars. We do about 8 of these sessions a month. And let us know if you've hit a roadblock in your dissertation and if you need further assistance. Just let us know. Have a great evening and take care.